figure out what I can put in there and how people are going to interpret it. Certificates are not just simple sequences of bits. These are complicated objects that have complicated languages. Like, will everyone parse the same thing in the same way? I thought about it, I'm like, no, there's no chance. There are patterns to security. One of the patterns of security is if you have a whole bunch of complexity, you're going to have a whole bunch of vulnerability. Certificates are fundamentally complex objects. Now, there are two kinds of vulnerability that you get from complexity. One kind is what I call traditional exploits. You cause the system to misuse memory. Inside of a certificate, you have large numbers of overlapping length fields. Overlapping length fields in a file format tend to instantly mean to a vulnerability researcher, okay, every parser is going to blow up. And in 2002, every parser did. 2002, SNMP was fuzzed by a company by the name of Cryptonomicon. Actually, no, it was fuzzed by the Protos project at the University of Jooli in Finland, who then went ahead and forked off this company, Cryptonomicon. They destroyed everything because ASN1, the underlying encoding for X509, and for SNMP, is a big mess. So all they did was throw random crap at it and blew up everything. But there's a second class of vulnerability, and this is something that hasn't been looked at much in certificates or in any of these ASN1 systems. And those are semantic exploits. This is when one person wins, because there's going to be multiple. There's this first one, www.badguy.com, and then there's this second one, www.bank.com. Which comes first? Which is the one that is trusted? Well, this is a problem for a text parser. This is also a problem for the certificate authority itself, because inside of an X509 public subject name, you could just have multiple common names. They could just be there. You know, you had an organization, so you have an organization, you have a city, you have a common name, you have a state, you have another common name, you have a organizational unit, you have another common name. You can just like throw multiple ones in there. What happens? It's a good question, actually. So I went ahead and looked. Well, it turns out that it totally depends on implementations, and all possible answers are implemented somewhere. OpenSSL trusts the first. Crypto API inside of Internet Explorer is all-inclusive, so if any CN matches, and Firefox takes the last. And the RFC says nothing. It has a two-word parenthetical that says use the most specific one without actually defining it. So the definition, first, all-inclusive, last, the definition actually is fail. Now, OpenSSL does not necessarily only return the first one. If you use the API in this particularly documented way, okay, if anyone ever tells you we had a security problem, but it's okay, we wrote some documentation and now it'll never be a problem again. I've heard that recently. So it's possible to use OpenSSL's API to do things securely, but no, everyone just uses this X509 get text by NID call. You see this in Clause and Open1X and wget and Bacula and Neon and OpenLDAP. Pretty much everyone just only returns the first common name. So if you have a CA that's using X509 name get text by NID, you're only going to see or validate the first common name. So how would you build the optimum exploit for this particular scenario? Well, it turns out you can have wildcards in a certificate. Netscape, if you have a cert for star, simply works for all names. It's the other way to say you're God. Internet Explorer, I gotta give them credit. They basically say, if some CA was stupid enough to issue this, I ain't touching it. Nice, that's great. So IE is chicken. They're only accepting wildcards if it's at least 2 labels in. So what you do is you have your first common name, www.attacker.com, and that's the one that OpenSSL leaves. And then you pick up a couple of websites. You can have however many you want. These are the ones in the middle, and IE gets those. And then you just throw in a star at the end for Netscape. So, now let's talk a little bit about ASN1, which I've kind of been, you'll cry. Yes, they did bit compression because you couldn't possibly use 2 bytes to express what would conveniently be 1 byte. Why? So, they have an incredibly stupid, I never thought I'd see stupider compression than DNS, but. So, okay. So you have 55 for 2.5, and then just a 4 for 4 and a 3 for 3. Very nice and simple. A more complex object identifier would be 1.2.840.113.549.1.1.1. Believe me, when they go crazy, they really go crazy. And yes, I'm watching the clock, making sure that I end this on time. So, tag 6, length 9. Now look what happens here. We have 8648. That means 6 times 128. Okay, that's larger than 80, so there's another digit. And 48 in hex is 72, so we get 840. That's how you end up encoding numbers in base 128 and expressing place value. You're using a bit to say there are more bits in this number. Works very well. So there's some ways of playing with this. The first thing you can use, and I think I've seen this before in LDAP, but if someone remembers, could you tell me? Because I don't know who to cite. I just know I've seen this before. Let's say you had leading zeros. You have a tag of 6, a length of actually 4. I got this wrong. 254. What if instead of just a 3, we do 8003? Well, now we have 0 times 128, which is still 0, plus 3. This is still 2543. It's just a different way of saying 2543. Wouldn't it be tragic if we had that in a X509 subject name as merely another field to ignore? What if this got through? Well, OpenSSL basically says, I don't know what the hell that is. That's good. NSS will actually parse it as 2543, but it will not say common name. It will say, I have an object identifier, it's 2543, but no, it's not common name. Internet Explorer is like, cool. This one made me really happy when it finally worked. Theoretically, numbers in ASN1 are infinite length. You can express 2 to the 5,000. In reality, ASN1 parsers are implemented on hardware, and hardware has limited sizes to the numbers that it likes to represent. This is usually a problem with memory allocation. I actually have a semantic equivalent. So what if we express the number 2.5.4.2 to the 64 plus 3? Which actually looks like this with all the zeros and a 2 and so on. Well, OpenSSL actually runs on a big num engine, so it is not fooled in the slightest. Netscape overflows, but not exploitably, because it also says the 2543. That was kind of sweet. Now, realistically, most certificate authorities do extract the common name and throw away the rest. At least now they do. That's good. Is there anything else malicious that we could get into the common name? Could we get something in that they really can't throw out? Well, a common name, you have an object ID, and you have an actual value, the ID value pair. And it's a printable string, usually. Say www.docsparrow.com, and that's just ASCII text.